Yes, so it's my pleasure to introduce today's speaker, Shumiao Wang. This is her fourth year as a PhD student at Purdue, and she's going to talk about a topic that's very important for the use of the cloud when without having to trust cloud servers.
Yes. Hi everyone, I'm Shumiao, and now I'm a PhD candidate working with Professor Atala. And today I'm going to present on my thesis topic, which is secure and private outsourcing to untrusted cloud servers. So first, I will present the motivation of outsourcing to cloud servers. And then I will present some techniques for general storage outsourcing and the techniques for computing without sharing, just in case that some of you may not be familiar with the topic. And after that, I will present our research problems on this, which include the shape-based feature extraction, the generalized matrix multiplication, and the server-aided secure and efficient co-design system. So, why do people use remote servers? I think there are a lot of reasons. For the clients who have very limited storage or battery life, as sensors, smart card, and cell phones, they don't have the ability to store a large database locally. So that's the reason why they want to use Amazon's products as S3 and other NoSQL services. They want to store their data at a cloud server, and later they will access the server, and to get back to retrieve their data. That's the first case of outsourcing, which is called storage outsourcing. Okay. And another kind of server, we want to do computational outsourcing. And such servers, they are limited in their computational power. They may like to use some products as the Google computer engine. And with such products, they can develop some code online and input their data, and then the Google servers will do all the computational work and return their data, return the result to the server, to the client. So that is called computational outsourcing. Okay, and another kind of clients may be lacking of softwares or professional supports. So such servers and such clients may want to use some products as app engine, which provides them many powerful development tools and SDKs. So I know a lot of companies that hold their online developing hackathon every year just to encourage their software engineers to use such cloud remote servers for development. And some clients may want to use a cloud server as a third party in the secure multi-party computation setting. I will give examples of this in our research problems. Okay. So as we can tell that using the cloud servers has so many advantages, such as they can reduce their cost, and it's very convenient, and they don't have to care about their SDKs and the management of their databases. So, but a lot of clients are still not willing to use cloud servers. That's because they do not want to review their information. So there are a lot of information reviews in the outsourcing setting. To the server, it may review the confidential data of the clients, and it may also review the answer that the server helped to compute. And to the clients, it may review the confidential data of the servers if the computation also involves the server's database. And it may also review other clients' data in a secure multi-party computation case. some clients are reluctant to review information because the input of their data may be some corporate strategy or some confidential scientific results. I know that a lot of scientific labs, they produce data as their as big matrices, and they want to use the cloud server to perform some computation on the large matrices. But they cannot send their matrix to Google because it's illegal to review their scientific results before publishment. So, and also some clients may fear of loss of control of their private databases, and some of them do not want to use their cloud servers because of their queries. Maybe it will cause him some embarrassment or some lawsuits. Now, I'm going to present the techniques for secure storage outsourcing. As I mentioned before, in secure storage outsourcing, the clients want to store his dataset on the server side, and later he wants to search over his database. But in this process, the clients do not want to leak his either the data or the query. So the first thing we can think about is how to hide the data from the server. The client can do this. He encrypts the data and then sends the database to the server. In this case, the server cannot see the data. But the question is, if he encrypts all the data, then how could he search over it? So a technique well used is order preserving encryption. So in this technique, the clients can encrypt their data points with such encryption schemes, and after encryption, the ciphertext will be at the same sorted order as the plain text. So in this case, it will enable the client to search even it is encrypted. But as we can tell that this kind of schemes can leak the order of the client's data. So it's some kind of leak, but it can protect of the data values, the real data values. And another kinds of techniques are tree-based. So in these kind of techniques, the client's partitions its data set using techniques as KD tree and organize them as trees. And then the clients encrypts the tree node by node and send the whole tree to the server. And when the client want to search in the database, he first fetches the root of the tree, and then he decrypts the root of the tree to see what informations are in the left subtree and what informations are in the right subtree. And because he knows his query, then he will follow the subtree that contains his query and go down level by level. So such techniques, usually such techniques will involve log n rounds of client-server interactions. And another technique that is well used is called basketization-based techniques. And in such solutions, the database are grouped into many baskets, and these will use the clustering algorithm in machine learning, and they cluster the data points into groups, and then divide the groups into baskets with basket IDs, and they will store the basket information at the client side. So in these solutions, it will demand some storage at the client side because he has to save some information for each basket. And another way is to secret transform of their spatial data. If the clients want to store spatial data, he can use some secret transformation functions of these data, transfer them into real values. And when they want to search, they just transform their queries. And this will involve some functions as Hilbert functions, which will provide the clients a way to query after transformation. Okay, so related work to the secure storage outsourcing, I have recommended reading is in their blog called Outsourced Bits. There are articles on the blog and introduces the current context of secure storage, how to search after encrypting, like that. Okay, and for the secure storage outsourcing, there are many applications as emails. So we all know that nowadays the email providers as Gmail, they do not encrypt our email contacts. So if you send somebody an email, actually the Google servers will store them in plain text. That's because this will enable us for quick search. Because in the email, we often search some keyword, so say homework, like that. So if you encrypt everything, then it's not easy for search. But such techniques in secure storage outsourcing, if the efficiency of the techniques can be improved, then we can apply them into the email products, and we can use them into the privacy-preserving data mining and location-dependent query processing for spatial data. And here are some techniques for secure computational outsourcing. This is also called server-aided computation because in this process, we are sending the input to the server, let the server compute, and then get back the results. So it's called server-aided computation. It's similar. In some ways, it's similar to the secure multi-party computation. Because the computed answers in both settings are of the same quality as if the private inputs had been fully shared. So they want the exact answers in this way. And the other requirement is in both settings is nothing is revealed other than the agreed upon computed answers. So they do not reveal their inputs, all the answers that they do not want to share. So this is the same thing. But outsourcing has additional assumptions than secure multi-party computation. The assumption is they assume the clients are always weak, so the servers are powerful. We want to put heavy lifting. We want the server does the heavy lifting and minimize the client's work. And another requirement is that we have to decrease the communication cost. So usually constant round of interactions between the server and the clients is desired. That's why the tree-based techniques are not so popular because they use log round of interactions. It will cost much more time. And so if we want the server to compute the values for us, we need techniques to hiding the values while enabling the server computing. There are some techniques to hiding the value, and we will use these techniques in our approaches. So these are just the building blocks. The first way to hide the value while enabling computing is additively splitting and sharing. So if the clients have a value x, and he can additively split it into two numbers. One is x prime, the other is x dot prime, and the sum of them is x. So if one party has x prime, another party has x double prime, they cannot get the value of x. But if they are willing to collaborate, then you can get x. So more generally, a Kn threshold scheming is that the value x is partitioned into n shares, and any more than k parties can recover x very efficiently, and any parties holding less than k shares cannot compute x. So that's the additive splitting scheme. And another technique is the homomorphic encryption. So in homomorphic encryption, the server can compute without seeing the true values. For example, there are two values x and y, and the clients can send e of x and the e of y to the server. Of course, the server does not have the decryption key, and the server can do a multiplication on the ciphertext of them, and which will give the server the encryption of x plus y. So this is the additive homomorphic encryption. There is another kind of homomorphic encryption called multiplicative, which means it will give you the product of x, the encryption of the product of x and y. Okay. And the third technique is secure circuit evaluation. This is a little complicated, so I will explain it into details. So the input of this is a function f and f x y, which this function is known to both parties. And x is the input of one party, let's say Alice, and y is the input of the other party, let's say Bob. So they want to compute f, x, y without leaking one party's input to the other. So how can we do this? First, Alice will build fx as a circuit. This circuit is just look like the electronic circuit. So some circuit may look like this. I will use this. So for some gate and some XOR gate. So these are the wires input to the gates, and they may involve some other gate like this and like this. So this is what a circuit look like. But generally, the circuit for a function is looks more huge than this. Okay. So Alice built this circuit, and then Alice chose two encodings for each wire. So there are, in this example, there are 1, 2, 3, 4, 5, 6, 7 wires. Alice should choose the encoding for each wire. Let's say this is this wire is called W. So Alice to choose a random binary string as W0, which represents the 0 value, and another W1 represents the 1 value for this wire, just for this wire. And for different wires, she just choose different random strings. And this is how Alice represents a wire. And for a gate, for any gate, Alice store four values for it. So let's take an example as an AND gate. Let's say the input values are U and V, and the output value is W. And Alice store 4 values to represent these gates, which are shown in the slides. So the first one is E with some message. Here I use OK, just denoting that whether the decryption is successful or not. E, OK, and concatenate with W1 with the encryption of this message with the key value U1 and V1. So why do we do this? It's because if some party has the encoding value of U1 and V1, let's say here has U1 and V1, which means the input values are of is 1 and 1. Then he can use these two strings as keys to try to decrypt all the 4 values. And we can see that they are encrypting with different keys, so only one of them can be decrypted. And by decrypted, it means it will show a message OK with some other random strings. And we can see that if you use U1 and V1 to decrypt all these 4 values, the first value will be successfully decrypted, and it will give you W1. So you cannot know W0 in this way. You can only know W1. And for the next gate, W1 will be part of the key to decrypt for the next gate. So that's how it works. So and this is the job at Alice's part. Alice just choose the encodings and represent each gate with 4 values, and then Alice will send the circuit, which means all the gates to Bob, and Bob receives the encoded circuit, and he has to get the encodings of all the input. And we know that the input there are 2 kinds of input. One is from X, Alice's input. The other represents Y, which is Bob's input. So for Alice's input, Alice can just hand Bob the encoding of her own inputs. Because the encoding of the inputs will not leak the real value. Bob does not know the encoding of each wire. So you send Bob, if you send Bob U1, Bob will not know it's U1 or U0 because they are randomly chosen. Okay. But for Bob's encoding, they have to perform an oblivious transfer to give Bob the encodings of his input. And we know that with oblivious transfer, Bob can ask Alice for either, let's say V is Bob's input. Bob knows the current V, the input should be 1, but he can use oblivious transfer to ask Alice for U1 for V1 without letting Alice know which one U1, V1 or V2 Bob got. Okay, so and then Bob knows all the input to the circuit, and then Bob evaluates the circuit gate by gate, as I showed earlier, and get the encodings of the output wires, and then they work together to translate what the meaning of the output wires to the values. This is how it works. So the secure circuit provides us a tool to let 2 parties compute a function together without leaking their private input. Okay. And now we are ready to present our research on outsourcing the shape-based feature extraction of images. So this problem is to find where are the appearances of basic shapes in a given image. This is widely used in the computer vision for detection purpose. So, for example, they can use this algorithm to detect specific shapes in a database of satellite images. You can find where are the straight lines and where are circles in the images. And the current algorithms involve heavy computational burden on a local computer. If you use a laptop to compute to extract the shape-based features of an image, it may take you several minutes. Here I present the traditional a traditional extraction example. So the left image is the original input image. So it's the image input into the system, and our goal is to find where are the straight lines in this image. This problem is called the extraction of the shape-based features. So find the parameters of the straight lines. So the traditional algorithm is called a half transform. So first, it transforms the image into an accumulation array based on the parameter space. So we can see that for straight lines, there are two parameters to represent a straight line in an image, which is the rho and theta. And the formula look like this. Rho is equal to x sin theta plus y cosine theta, like that. So we only need two parameters to represent a straight line. So in the left part, the image B is an accumulation array, and the index of the array, the two indexes, one is for rho and one is for theta. And for each rho and theta pair, in this space, it represents a straight line in the image. And what the half transformation do is, for each cell in the array, in the rho theta space, it counts how many non-zero pixels are there on the corresponding straight line in A. That's how they get the accumulation array. So let's take an example. If we can see a white point in the rho theta space, so in this rho theta space, the lighter the color is, means the value means the larger the value is. So it's a visualization. So we can see that the most largest value is corresponding to a rho near to corresponding to a parameter pair as theta near 0 and rho near 200. And if you draw this line on this picture, on the left side picture, you will see that this is the vertical line, and the other white point in the rho theta space is corresponding to the other line. So it's just a mapping from an image to the parameter space to the parameter space of the straight lines. So the claim here is, for this algorithm, each local maximum cell in the accumulation array is corresponding to a straight line in the image with parameters as the indexes in the array. So in this case, we can reduce the problem to find a straight line into finding maximum cells inside an array with real values. Okay. And this is how we can outsource this process to the servers, because as we can see in this transformation process, it will involve a lot of computation. We have to count for each rho theta parameter. So if you choose, if you want the result to be concise, and you will need a dense rho theta space, it will needs a lot of work to compute each cell in the accumulation array. So because it requires so much computational burden, that's the motivation we want to outsource. We want to outsource the image to a Google Cloud server, and let the server to find where are the straight lines for us. Here we do the outsourcing with two cloud servers. And first, the client, here in the picture, I show it as a data owner because there may be a lot of clients. They all can access the results. But in the picture, I show data owner, which is the clients who originally has the image, and the data owner first additively splits the image into two shares. Here, he splits the image pixel by pixel. For a pixel with number 0, he split it into two values, and the sum of them is the sum of the two shares are same as the original image. So he splits the images into two shares and sends one to each server. Now each server gets an image, but this image is meaningless because it's already splitted, and each pixel looks like a random number. So the server cannot gain any information about the image by seeing one share. And then each server performs a half transformation on its own share and obtains an accumulation array according to its share. This process is just as described before. They just perform the half transformation for each cell in the accumulation array, and they count and they just sum the value of the pixels on the straight line with the parameter. Then now the two servers, each of them has an accumulation array, but we know that the sum of the two arrays are actually the accumulation array for the original image, and the problem is they want to find the local maximums in the sum of the two arrays. And then in the third step, we know that to check whether a cell is to check whether a cell is a local maximum or not, it needs to compare it with all its 8 neighbors in the matrix in the array, and so each server prepares a 3 by 3 submatrices for each cell, which including it at the center and its neighbors surrounding it. And they prepare such matrices for every cell, and then they perform a blend and permute protocol on these sequences, on these two sequences. I will not go to the details of blend and permute protocol, but I will present the result of it. So if each party inputting a sequence of if each party inputting a sequence of 3 by 3 matrices, and the output of the blend and permute protocol will give each party also a sequence, and the outputting sequence is a permutation on the inputting sequence, while the permutation is neither known to the first server or the second server. So it's like permute the sequence for you without letting you know the permutation, but associated with each element in the sequence, it will provide you the encryption of its original index in the sequence. So, for example, if a cell is its order in the if a matrix its order in the original sequence is 3, it may after executing the blend and permute protocol, the order of it can be any number in the resulting sequence, but associated with it there will be an encryption of 3, and this key they should use a key known only to the clients. So the servers do not know the key of the encryption and the decryption of inside the blind and permuted protocol. Okay. And after that, the server has to check whether a cell is a local maximum or not. They do this by the secure circuit evaluation protocol we just presented, and I will give you the detail. So here are the examples of two. Here is an example of a 3x3 matrix shared by the two parties, and the coupled circuit protocol to evaluate whether A5 plus B5 is greater than all its neighbors is look like this, and the equal is just the equal is just the equal function of the circuit, and the results this circuit will give us a binary result, which means whether A5 plus B5 is greater than all its neighbors. So the server 1 and server 2 perform such circuit evaluation protocol for each submatrix and find whether the centering cell is a local maximum or not. If it is, then they store the encryption of its original index in the matrices, and if it is not a local maximum, they just discard the matrices, the small matrices. Okay, so they collect all the submatrices with their index information that have a local maximum central cell, and then at last the clients can interact with any server to get back the results, because the client knows the key to decrypting the indices in the sequence, so he can get back the indexes in the original matrix, and this will give them the row theta of the straight lines. Okay. And here is another research problem, which is how to outsource generalized matrix multiplication. The input to this problem is two n by n matrices A and B, which are holding by one client, and he wants to use only one server to compute the product, the generalized product of A and B, denoted by C, with the multiplication defined by min plus, plus min, or min max. And the plus times multiplication is known as the traditional multiplication. So in a traditional multiplication, any element in C, let's say Cij, is the inner product of the ith row of A and the jth column from B. So, and the inner product is defined as the sum of the products of each aligned pairs. And in our generalized product, we just modify the definition of the inner product. For each inner product of two vectors, the mean plus inner product is the minimum of the sum of each aligned pairs. So, and similarly, you can define the other two. And I think mean plus is more popular used as in the all pairs shortest path. So in the algorithm to compute the all pairs shortest path of a graph, we use this mean plus multiplication to iterate on the input matrix. So this is well used. So in this talk, I will only introduce how we compute the min plus, and the other two are similar but with different functions. And you can, if you are interested, you can check it in the paper. For min plus multiplication, the client in this protocol, the client performs a test for each possible value of the cell in the result C. So we have a range of all the possible values, and we call it a sigma. This is a parameter to our protocol. So the client check for each possible value. So a test is performed for all values from 0 to 2 sigma minus 2, and the test for value t is like this. For each cell in A, we expand it into a row vector with sigma length, because this is just written as, so this is just written it if as a vector of size sigma, and if the ALIG is 1, then if the L plus AI, the cell is less than the threshold T, then we set the AL, the bit, to be 1. Otherwise, we set it to be 0. And we do this for B, but we expand it in a column fashion. And we can prove that if we compute C, T means the expansion according to the value T. If we compute CT equal to AT multiply BT, this is the traditional multiplication. And then a cell in C equals to 0 if and only if the mean of the cell in the expanded value, if and only if the minimum cell in the expanded value is greater than T. So in this case, the client will check whether CTIG is equal to 0 or not. So it will set the smallest t that keeps the smallest v such that CVIG is not 0. So in this case, after performing this test protocol for all the t values, it will give us the minimum of the summation of the corresponding vectors in A and B. Okay. Here is another recent work on server-aided secure code designing. So in this problem, we have two companies. We call them Alice and Bob. They are co-designing a system like this. So Alice is responsible for designing the suspension system of a car, and Bob is responding to design the tires of a car. And they want each of the party has some parameters as denoted in the right half of the picture. So Alice has KFS and BF. These are just some parameters of the mechanical system, and they want to find out whether their design can work together. So this can be checked by checking a set of conditions on the stability matrix and the observation matrices. And these two matrices are in mechanical engineering are written in these parameters shown in the picture. And these, we know that we have two sets of parameters, and they want to compute some matrix together and then check whether it is a full rank matrix or whether all the eigenvalues of the matrix is negative. That's what they want to check. If it's full rank and the negative deficit and all the eigenvalues are negative, then they can and then they know that the system is stable and it works. Here is our security assumption about this co-designing system. We assume that adding a large value to add a large random to a value hides the value, and multiplying non-zero value by a large random hides the value. So, and at the beginning of the protocol, Alice and Bob first perform an additive split protocol for all the private input, because we know that the stability matrix is based on the parameters, and the parameters are holding by two parties. So first of all, they additively shares all the parameters by performing an additive split protocol, and then we provide a set of arithmetic protocols, and they are designed as building blocks, enabling Alice and Bob computes on split data with help from a cloud server. And these building blocks provide Alice and Bob compute as addition, subtraction, multiplication, division, and explanation. And also it enables them to compute a split data to compare a split data to 0 to check whether it's greater than 0 or less than 0. And it has been proved that such arithmetic protocols are complete in a computer system, which means if you can do the additions and the multiplication and the comparing with 0, if you can do such operations inside the system, then by reducing other computations to them, you can compute every operation in a computer. So then we provide high-level protocols to reduce the computation to a sequence of such building blocks, and we can reduce a full rank check by Gaussian elimination. And each step we use some arithmetic protocols, and we can also reduce our problem of negative definiteness check into a set of protocols to compute the determinant of matrices. And we know that the determinant of a matrix can be written as a polynomial of the elements inside the matrix. So because we can do the arithmetic operation, then we can evaluate the polynomial and check whether it is negative or not. And we implement this. We implement all the building blocks, and then we do the high-level computations by calling the functions of them, and then we can check. We checked this system. And we test that for some values given by Alice and some values given by Bob. We test whether their system works or not. And this is very fast due to, according to our experiments, we can do this system in about 100 microseconds. So it's very fast. So that's our work on the co-designing system. Okay, that's all. Any questions?
Thanks, the speaker first. Yes, time for some questions. So my only only suggestion would be to list the
I'm
conference.
sorry, could you use your microphone, please? Is that on?
I would suggest including some references, I think, to the papers and
Yes.
but
Okay.
this is
Okay.
this is
I will add the reference papers to the slides and then put it online.
online. Yeah.
Yeah.
I think that's very nice. Very nice work, Shumiao. So she will finish in 4 years. Thank you.
Thank you.